So this, as it turns out, is our last Chapter 10 lecture. Turns out we don't have to cover a whole lot of Chapter 10 to complete our Chemistry 11 curriculum. So yay for short chapters. And the topic we're going to be dealing with in this Chapter 10 lecture, right here, our last one, is intermolecular forces and liquid properties. So if you think back to our last lecture, one of the things you learned is that intermolecular forces are very weak in gases. We know the particles in gases are very, very, very far apart. So, clearly the IMFs must be weak because they're not being pulled together. Now, if we go back to our Chapter 5 notes and look at kinetic molecular theory, one of the postulates in kinetic molecular theory says that the IMFs are so weak in gases that they're to be considered negligible. And this means that gas particles are non-interacting. They neither attract nor repel one another because their IMFs are negligible. This also means that IMFs have no effect on gas properties. Now, things are quite different for liquids, and as it turns out, solids as well, but we're not looking at solids. One of the things we know, of course, is that IMFs are much stronger in liquids. And because of this, we're going to be able to observe that they do have an effect on liquid properties. So we're going to be taking a look at the relationship between IMFs and some important liquid properties. I want to note that I am skipping one liquid property in particular that is discussed in your textbook, and that is the property of capillary action. So I decided we're not going to discuss that, but we are looking at the other properties. So the first liquid property we're going to deal with is right here. It's called viscosity. And viscosity could be described or defined as the resistance of a liquid to flow. Now, what does that mean? Well, let me give you an example to sort of illustrate exactly what that's all about. Let's consider two liquids, alcohol, and neither of these are pure, versus, say, honey, alcohol and honey. Now, when we compare how these two liquids behave, how they flow, well, we could say that the alcohol, flows quite freely. It flows readily. So let's write that. Flows easily. Especially if you're at a bar. No, I'm just joking, right? The alcohol does flow easily at bars, though. Let's move on to honey. Well, when we try to pour honey, it doesn't flow very well. It takes a year and a day for the honey to move from one location to another. So we could say that the honey does not flow easily. Now, since the honey does not flow easily, what is it doing? It resists flow. That's what it's doing. Resists flow. And since the honey is resisting flow, we would say that the honey is a more viscous liquid with a higher viscosity. So this is a more viscous liquid, and it has a higher viscosity compared to, say, alcohol, which flows easily and is therefore a less viscous liquid by comparison, and has a lower viscosity. So now you've got an idea of what that definition of viscosity is all about. Well, what are the role of intermolecular forces? Well, as it turns out, liquids with stronger intermolecular forces tend to be more viscous than liquids with weaker intermolecular forces. In other words, as IMF strength increases, so as IMF strength goes up, what happens to viscosity? It also goes up. Viscosity also goes up. And you know what I'm going to do? I'm going to put little stars around this little relationship here, very useful. And I'm going to highlight. Let's highlight this relationship. Okay. So why is that the case? Why would stronger intermolecular forces lead to liquids being more viscous? Well, in order for a liquid to flow easily, the particles, the molecules of that liquid need to be able to glide or slide smoothly past one another. Now, if IMFs are stronger, those liquid molecules are attracted to each other. So it's like they stop and group up a little bit instead of sliding past one another easily. And so if IMFs are stronger, all right, we are preventing the liquids from molecules from sliding past each other. And this, of course, is impeding their ability to flow, which causes a higher viscosity. Okay, let's write some of that down. So let's note that this, oops, I'm not going to write with a highlighter. I have to write with a regular pen. So I'm going to note here when liquids have stronger IMFs, their molecules cannot easily slide past each other. Their molecules cannot easily slide past each other. And of course, this, of course, is going to impede flow. So thus impeding their ability to flow. Okay, so we've seen the relationship between IMF strength and viscosity. There's something else that I wanted to note here, and that is that liquids that are composed of longer molecules also tend to be more viscous than liquids composed of compact molecules. So I'm throwing this in here again for those of you who are going to eventually move on to organic chemistry. And, well, the liquids you work with in organic chemistry are going to have a variety of viscosities. And it turns out this is an important correlation that is going to be important, at least, when you get to organic chemistry. So then the question is why? Why would liquids composed of longer molecules tend to be more viscous? Well, think about long molecules. All right, what can they do? They can get tangled up with one another. And if they're tangled up with one another, they're not going to slide past each other very well. And so longer molecules, more entanglements lead to impeded flow. And that's why these liquids tend to be more viscous. So I'm going to write that little explanation down for you as well. So I'm going to say that longer molecules are more likely to get entangled and of course this impedes flow. Okay, so the last thing I'm going to note here about viscosity is the relationship between viscosity and temperature. And it turns out that as temperature is increased, at higher temperatures, liquid viscosity decreases. That means as we raise the temperature, all right, the liquids get less and less viscous. Their viscosity is going down. And if they're getting less and less viscous, that means that the liquids are flowing more easily at higher temperatures. And I think this is something that most of us have actually observed in real life. I at least always observe it with shampoo. So if it's really cold in the bathroom, all right, the shampoo tends to be very thick and viscous and doesn't pour easily. But I don't know, maybe you have a window by your shower and you leave the shampoo at the window where the sun hits it and warms it up all day. And if you go and try to pour the shampoo at the higher temperature, it's positively runny. It's just running right out. So, well, why? Why is this happening? Well, first, let's just write this relationship a little bit more concisely. As temperature goes up, viscosity goes down. That's the key relationship here. And I'm also going to put little stars around it, highlight it. Yay for highlighting. But what's going on? Well, let's think about this. At higher temperatures, the liquid molecules are going to have higher kinetic energy. And if they have higher kinetic energy, all right, that higher kinetic energy, all right, can be partially overcoming the intermolecular forces. And so if we can overcome those intermolecular forces, well, what's going to happen is, yes, it's going to be easier for the particles, the molecules, to glide past one another. So let's note, all right, the molecules of the liquid have higher kinetic energy at higher temperatures. And the higher kinetic energies will partially overcome the IMFs. All right, so let's write that, which can partially overcome the IMFs, which would allow the liquid to flow more freely. Okay. Well, that's our first liquid property that was on my list for this particular lecture. Viscosity is now done. And the second property we're going to take a look at is something called surface tension. So I have the definition of surface tension right here. It is the tendency of a liquid to resist increasing and thus minimize their surface area. It really should say its surface area. Let's correct this. There we go, too. So let's read that again. It's the tendency of a liquid to resist increasing and thus minimize its surface area. So to get a sense of what surface tension is all about, to understand that definition, what I've done here is a schematic representation of a liquid. I know it might not look like that. Each blue dot represents a liquid molecule. Now, the liquid molecules are playing different roles. Some of those liquid molecules are right here at the top, and these are what we call surface liquid molecules. On the other hand, the rest of the liquid molecules, which are found in the bulk of the liquid, we could call these interior liquid molecules. Now, all of the liquid molecules are attracted to one another, but they're not attracted to one another equally. For example, let's take, and let's actually just identify these molecules first. So I already said that these ones up here are our surface liquid molecules versus the rest of the molecules. I'm going to use different colors here to help me out. So all the rest of the molecules here, we could call these interior liquid molecules. So let me take one of our interior liquid molecules. For example, let's take this molecule right here. Now, this little molecule is going to experience intermolecular forces with all of the other liquid molecules that surround it. In other words, there's going to be an interaction between this molecule and an IMF interaction between this molecule and this molecule and this molecule and this molecule and this molecule. And so it is essentially experiencing these intermolecular force interactions in all directions all around it, which is very stabilizing. And as a result, because these interactions are so stabilizing, interior liquid molecules have lower potential energy, low potential energy. So I'm going to write low potential energy due to many stabilizing interactions with surrounding molecules in all directions. Now, things are a little different for our surface liquid molecules. So I'm going to pick a surface liquid molecule. Let's pick this one right here. So I'll do this one in red. So I'm color coding for us. Now, this molecule is also going to be experiencing intermolecular forces with surrounding molecules. But when we take a look at which molecules it can interact with, well, there's one over here, and to the left, and down here, and down here. So let's note that there are fewer stabilizing interactions for the surface liquid molecules. Also, that if we consider the intermolecular forces to the left over here and the right over here to cancel, this means that the surface liquid molecules are essentially being pulled. There's a net pull of our surface molecules towards the interior of the liquid. Okay. Now, this is going to result in our surface liquid molecules having higher potential energy. So higher potential energy. They're just not as stable as those cozy interior liquid molecules are. So I'm going to say higher potential energy. And this is again due to having fewer stabilizing interactions. In other words, we could simply say that our surface liquid molecules are ultimately a bit less stable than our interior liquid molecules, which are clearly more stable down here. Now, liquid molecules are in constant motion, so they're not locked into fixed positions. So they're moving around. Liquid molecules are moving around. Interior molecules are moving around. Now, this is where we get to that definition of surface tension. Since those interior liquid molecules are much more stable, they don't want to move into a surface position, because if they move into a surface position, they become less stable. So when we look at that definition that says that surface tension is the tendency of a liquid to resist increasing its surface area, what's going on? Well, the liquid molecules that are interior resist moving into a surface spot. So if they're not moving into the surface spot, there's going to be less surface liquid molecules. In fact, a liquid works to make sure it has as few surface liquid molecules as possible because of their higher potential energy. And this means that the liquids work to have a very low surface area. Low surface areas will have as few as possible surface liquid molecules. And the reason is because those interior molecules are not going to be moving to the surface if they can help it at all. So I'm going to write that up here. So I'm going to just say the interior liquid molecules resist moving to the surface. And this means that a liquid works to ensure that there are as few surface molecules as possible, which gives a liquid the minimum possible surface area. So let's now, let's try this again with the right eraser here. All right, so there will be as few as possible molecules at the surface, which minimizes the surface area. So I'll just squeeze that in here, minimizing the surface area. And I'm abbreviating surface area, SA, surface area. I want to note that this particular property of liquids, to try and minimize their surface area, to keep as few liquid molecules at the surface because the interiors are staying where they are, this is why liquids tend to form perfect spheres, all right, when they're as droplets, perfect spheres. A perfect sphere, as it happens, has the lowest possible surface area. It's the one geometric, three-dimensional geometric volume that has the lowest possible surface area. And that's why they form droplets. Now, what is the relationship between surface tension and intermolecular force strength? Well, that's right here. Liquids with stronger intermolecular forces have higher surface tension than liquids with weaker intermolecular forces. In other words, as IMF strength goes up, surface tension also goes up. And I'll also, let's star this in yellow so it matches what we did before. Star, star, and highlight. So why would this be the case? So why are those interior liquid molecules so stable? Because they're interacting with all the surrounding molecules. And so if those interactions are stronger interactions, that makes those interior liquid molecules even more stable and thus even more resistant to moving to the surface. So that's what's going on here with our IMF strength and surface tension. Okay, so our next look at liquid properties deals with, well, it deals with a few things we're going to be dealing with here. We're going to start by looking at what happens when liquids vaporize in a lot more detail. This is, of course, an important phase change that liquids undergo. Liquids can vaporize. And a related concept to liquid vaporization is vapor pressure of liquids. So we're going to be looking at these two in turn. Now I'm going to start with what vaporization is. Well, vaporization is a phase change. And what phase change is it? It's right here. It is the liquid to gas phase change. But we need to qualify a few things about this phase change. Turns out vaporization can only take place at the surface of a liquid. Only surface molecules vaporize. Now, what criteria must be met for a surface liquid molecule to vaporize? Well, as it turns out, it can occur at any temperature. So liquid molecules at the surface can pop off and become gas molecules at any temperature, but the caveat is that those surface molecules must have enough kinetic energy to overcome the IMFs in the liquid and break free, and pop off into the gas phase. Okay, well, let's take a look at this in more detail. So for starters, we know that the only liquid molecules that matter in vaporization are these at the top, are surface, not the interior ones at the bottom. Now, I showed you a little while ago that the net effect of all of the interactions experienced by surface liquid molecules are primarily in a downward direction. So we can think of all of these surface liquid molecules essentially being pulled towards the bulk of the liquid, towards the interior molecules. So let's just write something about that over here. I'm going to say that IMFs attract surface molecules. Another way to say that is pull surface molecules. They're attracting the surface molecules towards, well, towards the interior molecules. Okay. Now, not every surface molecule is going to be able to vaporize. Turns out that all of the molecules at the surface have a range of different kinetic energies. So kinetic energy is the energy of motion, and of course those liquid molecules are moving around and therefore they have kinetic energy. Well, if we examine all the kinetic energies of all the surface molecules at a given temperature, what we see is that there is a distribution of kinetic energies. And in fact, this kind of distribution is one that we've learned about before when we're studying gases. It's called a Maxwell-Boltzmann distribution, kind of like a bell curve, but definitely not exactly the same. So what does this curve represent for us here? Well, at a given temperature, and this curve does change a bit if we change the temperature, but at some given temperature, well, let's have our y-axis be the number of surface molecules, because that's what we're looking at here. It's only surface molecules that matter to us right now. And on our x-axis, we've got the kinetic energies of all the surface molecules. Now, what we can see here is some of the surface molecules have very low kinetic energy. Some have very high kinetic energy. Most of them have kinetic energy in the middle. Now, in order for a surface molecule to be able to vaporize, it has to have enough kinetic energy, some minimum kinetic energy, to break free. I need to be free. So let's suppose randomly that right here, this represents right here the minimum amount of energy a surface molecule must have in order to break free. So let's note that this is the minimum energy to overcome IMFs and vaporize. That means only the molecules with kinetic energy higher than the minimum are going to be able to vaporize. So just these ones, these are the molecules that can vaporize. So only a few can vaporize. And that's because they have enough energy. They have above the minimum energy. Their kinetic energy is high enough. So if we go back to our surface, well, let's suppose this little molecule has high enough kinetic energy, or this one has high enough kinetic energy to overcome and break free of those red intermolecular forces pulling it back. Well, these can break free. So I'm free. And this one's I'm free, and I'm free. And okay, well, now we can see. And let's draw them over here, being little free molecules. Now they're now entering in the gas phase. And this is the process by which liquids gradually vaporize. So every layer of liquid, every new layer of liquid that is exposed, only a few of the surface molecules which have enough kinetic energy can break free and become gases. And of course, this is an open container. And so in the end, these particles would take off into the atmosphere. Now, we can look at how fast liquids vaporize, the rate of vaporization. And when we analyze how quickly or the rate of how quickly liquids vaporize, we find out that there's certain factors that affect how quickly the liquids vaporize. And there are three important factors. One is surface area, two is temperature, and three is intermolecular forces. So let's look at each of these in turn. Turns out that as the liquid surface area goes up, I'll write SA for surface area goes up, the rate of vaporization also goes up. So surface area is how much area, all right, of the liquid is exposed to air at the surface. So let's suppose we have a liquid in a tall, thin glass, a liquid like water. Now, if we left that glass of water out, All right, sitting in your kitchen all day long. Well, what's happening? Well, the molecules of water are absorbing heat from the surroundings. Maybe not a whole lot of heat because your kitchen is probably not too hot, but some of those surface liquid molecules end up getting enough heat absorbed to increase their kinetic energy so that they're popping off. Okay. Now, let's suppose instead of the liquid vaporizing out of that tall, thin glass, you took the water and poured it on the ground. So now the water is in a puddle shape. Okay. Where is the surface area higher? The water in the glass or the water in the puddle? Well, of course, the surface area is much, much higher in the puddle. So what's going to happen? We're going to see the puddle disappear faster. All right, as the rate of vaporization is much higher than the rate of vaporization for the same amount of water in the tall, skinny glass. The only change has been surface area. So what's going on here? Well, if the surface area is increased, we simply have more liquid molecules at the surface. So vaporization is going to occur, all right, at a higher rate. So I'm just going to write that down over here. So more surface liquid molecules leads to increase vaporization. Now, the second effect we're looking at is the effect of temperature. And well, once again, we're going to see that as temperature increases, the rate of vaporization again increases. So temperature is not changing the numbers of surface liquid molecules, but what temperature will do is it will change how many of those surface molecules can escape. Why? Well, if we raise the temperature, what we're doing ultimately is increasing the kinetic energy of the surface molecules. And if the kinetic energy of the molecules is higher, that means more of them are going to be able to escape, increasing vaporization. So I'm going to write this down here. So higher temperatures cause higher kinetic energy in our surface molecules. And if they have higher kinetic energies, that means that more will be able to break free and vaporize. And so this, of course, leads to increased vaporization. Oops, I should say increased vaporization rate. So the third factor is intermolecular forces. And specifically, I mean the strength of the intermolecular forces. And so in this case, what we're going to observe is that as the IMF strength between particles increases, the rate of vaporization actually decreases. It decreases. So what was the role of the intermolecular forces again? Well, they're right over here. They're pulling the surface molecules towards the interior molecules. So if those IMFs are stronger, they're pulling harder on those liquid surface molecules. And of course, that's going to make it harder for surface molecules to escape, leading to a decreased vaporization rate. So let's also make a note of this over here. So if, whoops, I didn't mean to do that. There we go. If IMFs are stronger, fewer surface molecules, oops, let's try that again. Fewer surface molecules can break free, and so this leads to a decreased vaporization rate. So now we understand a little bit more about the process of vaporization that's taking place at the liquid surface and some of the factors that affect the vaporization process. Now, things become a little bit different if the liquid that we're looking at is now in a sealed container. So I'm going to put a star right over here. The liquid is in a sealed container. Well, this picture doesn't have a sealed container, so let's put a cap on it. There we go. Let's seal it up. So if the liquid is in a sealed container, what are some of the differences that we're going to notice? Well, once again, the only molecules that can vaporize are those surface molecules with enough kinetic energy. So once again, let's suppose that this molecule has enough kinetic energy and this one and this one. Okay, well, they can start popping off. Okay. Now, interestingly, where we're going to see things initially. So if surface molecules are popping off, okay, so now they're over here and here and here. What we initially see is that there is, I'm going to put a little star here too, we're going to notice that the liquid volume starts to drop a little. So the liquid volume decreases, but it only decreases slightly. Now, the liquid volume is decreasing because we're removing layers of liquid from the surface. Now, what's happening to that liquid? It's becoming gas. And so in this space above the liquid, this space on the top here, well, that space is having a buildup of gas within that space. And that's because, of course, the container is sealed. The gas cannot escape into the atmosphere. So I'm going to also note that gas builds up in the space above the liquid. Okay, so more and more of the liquid is vaporizing, and well, we're getting more and more gas molecules. Okay, well, what do we know about gases? Well, we know the particles of a gas are in constant random motion. They're in constant random motion. And so these gas particles are banging about. This one's going to smack in over here, and then it's going to change direction, etc. This one's knocking up here before it changes direction. Now, obviously, some of these gas molecules, as they bump around, are going to start to collide with the liquid surface. They're going to collide with the liquid surface. And when they collide with the liquid surface, well, what's the opposite of vaporization? Condensation is what's going to occur. These gas molecules that collide with the liquid surface are being recaptured by the liquid, and they condense. So the gas is converting back to a liquid. And so two processes are taking place simultaneously. Surface molecules are turning into gas, and the gas turning back into a liquid. Now, eventually, the rates of these two processes will be the same. The rate at which the surface liquid turns into a gas is going to equal the rate at which the gas is turning back into a liquid. And when this scenario is achieved, when we get these two rates to be the same, well, what do we notice? Well, we notice that the liquid volume stops decreasing and it stays the same. And we also notice that the gas quantity above the space, which was building up, stops building up and stays the same. And so I'm going to note this. All right. So volume of the liquid stops decreasing, stays constant. And the amount of gas no longer builds up. But stays constant. Okay. And so now we're going to have a constant amount of gas in the space above the liquid in the sealed container. Now, what do gases do? Well, gases exert pressure. Gases exert pressure. And we call the pressure exerted by the gas above the liquid the vapor pressure of our liquid. That's called the liquid's vapor pressure. And we can measure it in normal pressure units such as atmospheres or torr or millimeters of mercury. Because we get this pressure under equilibrium conditions, we sometimes refer to this as the equilibrium vapor pressure. So I'm going to write that over here. So the equilibrium vapor pressure is the pressure exerted by the gas above the liquid. When this conditions of rate of liquid to gas equals rate gas to liquid, only when these conditions occur. And the equilibrium vapor pressure is often abbreviated with symbol P subscript VAP, PVAP. So now we know what vapor pressure is. The pressure of the gas that collects above the liquid as a result of two processes taking place: surface liquid to gas, gas back to liquid. When these processes are at the same rate under equilibrium conditions, the amount of gas that we end up with is exerting a pressure, and that is our vapor pressure. Woo! Okay. Now that we know what vapor pressure is, and all liquids will have a vapor pressure if they're in a sealed container. Now, as it turns out, if two liquids are compared at the same temperature, okay, it turns out that the liquid with stronger IMFs will always have a lower vapor pressure than the liquid with weaker IMFs. In other words, as IMF strength goes up, vapor pressure goes down. So let's star this and highlight this. Starring, highlighting. So what's going on here? Well, if IMFs are stronger, do the liquid molecules want to vaporize? Well, not particularly. It's going to be much harder for the liquid molecules to vaporize. And if the liquid molecules aren't readily vaporizing, are we making more gas or less gas in the space above? Well, we're going to have less gas. And if we have less gas, we're going to have a lower vapor pressure. So let's note that over here. If we have stronger IMFs, lead to less liquid vaporization and less gas above the liquid. And of course, less gas exerts a lower pressure. Okay. Now it turns out we have a special name for a liquid that has a higher vapor pressure than another liquid. We say liquids with higher vapor pressures are more volatile liquids. So if we say a liquid is more volatile, it has a higher vapor pressure. And less volatile would mean that the liquid has a lower vapor pressure. Volatile. There we go. And I'm also going to highlight that because that's kind of important. So a more volatile liquid will have a higher vapor pressure, and a less volatile liquid will have a lower vapor pressure at the same temperature. Now, Just as IMFs have an effect on the vapor pressure, the equilibrium vapor pressure of a liquid, turns out temperature also has an effect on the vapor pressure of a liquid. And what is that effect? Well, it's right here. As the temperature of a liquid goes up, the vapor pressure of the liquid also goes up. Higher temperatures, more liquid molecules vaporize, leading to more gas collected above the liquid and higher pressures. Now, if we measure the vapor pressure of a liquid at different temperatures and then create a plot, what we end up with is called a vapor pressure curve. And over here, I actually have a plot of gas vapor pressure above a liquid versus the liquid temperature. And you can plot them in different units. In this particular plot, the vapor pressure is measured in torr, the temperature is in degrees Celsius. And what I actually have here is the vapor pressure curves for two different liquids, where the first liquid, excuse me, for this curve over here is liquid chloroform. And the second curve over here is for liquid propanol. And so for both of these liquids, we can see as we increase the temperature, what's happening to vapor pressure? It's also going up. As we increase the temperature, the vapor pressure is going up for these two liquids. And we'll always get a similar curve to this for any liquid for which we plot vapor pressure versus temperature. All liquids will give us these curves. Now, turns out we can get some important information by looking at vapor pressure curves. For example, one of the things that we could figure out from these two curves is which of these two liquids is more volatile. So, which liquid is more volatile? So, does a more volatile liquid have a higher vapor pressure or a lower vapor pressure at a given temperature? Well, it's going to have a higher pressure. So, equals higher PVAP. So, all we have to do is pick a temperature. Pick any temperature you want. So, let's pick a temperature of, say, 40 degrees Celsius. Okay? Well, at 40 degrees Celsius, the vapor pressure of propanol, here, I'll use green here, propanol is under 100 torr, but the vapor pressure of chloroform is close to 300 torr. So in this case, chloroform has the higher vapor pressure than propanol at every temperature along this curve. And so our answer here is chloroform. So our answer here is chloroform. So let's just note here at 40 degrees Celsius, PVAP for chloroform. Let's just make myself a little clearer here. So PVAP for chloroform, I'm going to say it's about, I'm going to guess around 300 torr, whereas PVAP for the propanol at the same temperature, is it's less than 100 torr. Is what we can see from this graph. So that's one bit of information we could get from looking at the graph. All right, which liquid is more or less volatile? Here's another question we could ask. Which liquid do we believe has the stronger intermolecular forces? Okay, well, let's think about the liquid that's more volatile and has the higher vapor pressure. Will a liquid have a higher vapor pressure and be more volatile if it's got stronger IMFs or weaker IMFs? Well, the answer is weaker IMFs. If the IMFs are weaker, we get more vaporization, more gas, higher vapor pressures, which means that in this case, the liquid which has the stronger IMFs must be the liquid with the lower vapor pressure. So this would be equal to, oops, why am I getting this here? Okay, I did not mean to do that. Let's try this again. So this equals the liquid with the PVAP being lower, and the liquid with the lower vapor pressure throughout is, of course, propanol. So things that we can get from a vapor pressure curve. Turns out there's one more important thing we're going to be able to get from a vapor pressure curve, which we're going to see very shortly as I scroll down. So far, all I've been talking about is vaporization, the process of vaporization. Now, I want to be very clear that the process of vaporization is not identical to the process of boiling a liquid. So vaporization, what we've learned so far, is ultimately the liquid to gas phase change that takes place where? It takes place at the surface of a liquid. And it can occur at any temperature, provided our molecules at the surface have enough kinetic energy. Now, a liquid boiling is something different. A liquid boiling is still a liquid to gas conversion. But let's think about what we observe when we see a liquid boil. For example, boiling water. Everybody has boiled water. And how do you know when the water is boiling? It's not because you see steam coming off the surface. That's not when the water boils. We know the water is boiling when we see those big fat bubbles in the water. So there's a bit of a difference. It's not the same as vaporization, is it? Well, it turns out, if we're thinking about this process very carefully, a liquid can only boil when the vapor pressure of the liquid equals atmospheric pressure, which, depending on your units, 760 torr, 1 atmosphere, 760 millimeters of mercury, etc. In other words, I'm just going to write that here, that P vapor must equal P atmosphere for a liquid to boil. That's what we're saying here. Okay, so let's think about the heating of a liquid. So we're heating our liquid up, and what happens to the vapor pressure? It's getting higher and higher and higher. And why is it getting higher and higher and higher? Because more and more gas is being produced above the liquid. Now, at some temperature, the pressure of the vapor is going to balance atmospheric pressure. Now, this is really important for boiling. For boiling, interior liquid molecules need to be able to vaporize. Now, they weren't able to vaporize before because atmospheric pressure was too strong, was too large. So every time those liquid molecules in the interior tried to vaporize and make bubbles, atmosphere smashed them flat. Boom. Now, when the vapor pressure of the liquid is high enough to balance atmospheric pressure, well, this is now going to allow those interior liquid molecules, in addition to the surface molecules, to finally be able to vaporize and form bubbles of vapor in the liquid bulk, which is when we know the liquid is boiling. Now, this couldn't happen until the vapor pressure of the liquid balanced atmospheric pressure. Otherwise, atmosphere flattened those interior bubbles. Now, the temperature at which this occurs is known as the normal boiling point of the liquid. Okay. Now, using a vapor pressure diagram like the one I have up here, all right, we could actually use it to estimate the normal boiling point of both chloroform and propanol. So the boiling point of each of these liquids would be the temperature at which the vapor pressure of the liquids equaled atmospheric pressure. Okay, so let's note that vapor pressure here is in torr, and atmospheric pressure in torr is 760 torr. So I'm going to draw a line here. Let's use blue. 760, well, 700 is in the middle here, and so 760, I'm going to guess that 760 is about here. I'm obviously making an estimate. So what does this line represent here? So this line here is when PVAP equals P atmosphere, which is 760 torr. Now, the temperature at which this occurs for each liquid is that liquid's boiling point. So for chloroform, okay, well, the temperature at which chloroform's vapor pressure equals the pressure of the atmosphere is roughly 60 degrees Celsius. And for propanol, right here, where it intersects, the temperature at which the vapor pressure of propanol equals atmospheric pressure is a little bit above 80. We could call it maybe 82 degrees Celsius. So this over here would be the boiling point of chloroform. And you know what? Let's color code it. I was color coding it green versus red. So let's keep with that color coding thing. There we go. And this would represent the boiling point of the propanol. And so I'm going to write that down over here, that for example, all right, from the figure above, we could get that the boiling point of chloroform is approximately, obviously we're making an estimate, 60 degrees Celsius, while we're going to estimate the boiling point of the propanol liquid to be approximately, I'm going to go with 82 degrees Celsius. Okay, so we're now done discussing intermolecular forces in liquids, and we're done with all of the sections of Chapter 10 that we need to do in our Chem 11 course. Okay, great. So everybody take care, and for now, goodbye.